Remember, these recordings will be available in this week's module. I'm now recording on my computer, so there's no need for a passcode or anything like that. So no need to inquire about it. This recording will be posted later tonight. And now for Wednesday, there is no virtual class on Wednesday, day before Thanksgiving. I'm going to be pre-recording the topic on Wednesday, which is an introduction to hypothesis tests. So that will be pre-recorded, and I will post it later on Wednesday, later, probably by the night. It should be posted. So you can view it at any time, but make sure you view it before next Monday's class. There is
Professor.
a quiz. Yes. Yes.
The recording you posted last weekend, when you try to click on it, it don't come up. It don't come up at all. It's just blank.
It's blank. How many people? Anybody else have that problem? Which one was it? Which one?
I just for me.
Last Wednesday or last?
The 18th. No, it's coming. No, for the 18th last Wednesday. This weekend I was trying it. It would come blank, but I guess when you give it a chance to load up, or I don't know. I guess my internet wasn't working good, but it's coming up now. It's coming up now.
All right. Okay, good. Because I do test it. I make sure that they are available before. I mean, it works before I post it. Okay, good. So today what we're going to do is I'm going to do a review of what we covered so far with hypothesis tests, and also show you two additional types of hypothesis tests. I'm going to be starting the quiz a little bit early today. Should be starting at 10 after 4, as opposed to 20 after 4. I'm giving you all an extra 10 minutes, so it'll be a half an hour for this quiz. And it will cover, and I was able to figure out how to copy and paste stat key graphs into Canvas, into a Canvas quiz and test, of course. So you should be able to see it okay. It's a little small, but I was able to see it. The quiz will be like the other ones. The only difference is that the last question will be a true-false question, and it'll be 4 points for the true-false question. The first 4 questions will be fill in the blanks as before. You can use StatKey, to see how it works. You can use your textbook, any notes that you have when you take the quiz. Make sure you have some sort of calculator just for simple arithmetic type calculation, which I will show you as I do my review. So review should give you everything you need to know for the quiz, plus a little bit more. All right, so the first thing I'm going to do is go to the textbook, share the textbook. All right, and so in chapter 20, the whole chapter deals with confidence intervals for proportions, but you only need to know the first 2 sections, or read the first 2 sections. And there's really not a whole lot to go over here, but I want to just make sure that you understand what a confidence interval is. And then I'll talk a little bit about the traditional way of doing confidence intervals through formulas. And then we'll go over StatKey again, what StatKey is. Now, a confidence interval is an interval of values that is there to estimate either a population proportion or a population mean. In this chapter, it's just proportions that we're dealing with. So it's just an estimate, and it's a range of values. Hold on 1 second. Now, how do you calculate it? Well, if you were going to use formulas, the calculation, there's several steps, but in essence, the calculation involves taking your sample proportion. In this chapter, it's a sample proportion, but it could be sample mean, and you add and subtract from it what's called the margin of error, all right? The margin of error. So the margin of error is when you subtract it from the sample proportion, you get the left end of the confidence interval, and when you add the margin of error to the sample proportion, you get the right end of the confidence interval. And that's the traditional way of calculating it. Then you have to figure out how to calculate the margin of error, and there's a formula for it. And the formula, basically, the first thing you have to do, and again, you're not responsible for this, but you would take the square root of the following formula, which is the proportion times 1 minus the proportion divided by the sample size. You take the square root of that whole thing. And then you would, that's called the standard error. And then you would, traditionally, you would multiply that standard error by a multiplier, okay? So some multiplier, one of the multipliers like these here. And the multipliers are determined by the confidence level. Confidence level has its own, each confidence level has its own multiplier. So you take your multiplier, multiply it by the standard error, and you get your margin of error. Then you add and subtract it from the sample proportion, and you get your confidence interval. So we're not going to be doing that in this course, but I just wanted to show you the formula way of doing it. Now, confidence level, of course, you do need to know what that means. So we'll talk about that in a minute. So this is the formula, the formulaic way of calculating it, which you would do if you were taking a traditional statistics class. All right. And then in the next chapter, chapter 20, let's just go out of chapter 21, is dealing with confidence intervals for means, for estimating population means. So the first thing you would do is calculate what's called the standard error for a population mean or sample or distribution, frequency distribution of population means. And you take your population standard deviation divided by the square root of the sample size. Again, you're not responsible for that. You're not going to be using a formula. And then you multiply it by that multiplier. All right, the multiplier times this formula here will give us our margin of error, and then you add and subtract that from the sample mean in this case, because you only have one mean, one sample, one mean, and that's how you would create your confidence interval. This is the traditional way of doing it with a formula. So we're not doing that in this course. We're using StatKey instead. So just give me a second here and find StatKey. Sec here. All right, so this is StatKey. All right, so you all probably, I hope, have already played around in StatKey a little bit. Again, you just type in StatKey into your browser, you'll get to, it'll say something about Lock. Lock is the family, the Lock family are the ones who created StatKey and created the textbook built around it. So StatKey does confidence intervals, but not in the traditional way using formulas. It uses this procedure called bootstrapping, which I'll describe it again in a minute. So suppose we wanted to create a confidence interval for a single proportion. So we would click that. And suppose we create our own data set, data. Suppose we have a sample size of 2,000. And suppose 1,200 of the 2,000 said they were interested in voting for candidate A versus candidate D. So we'll click OK. Notice that 1,200 divided by 2,000 is 0.6. That's our sample proportion. This is our one sample. We sampled 2,000 people. We've asked them the question, who do you prefer, candidate A or candidate B? And 1,200 of the 2,000 said candidate A, which means 800 of the 2,000 said candidate B. So what is the proportion of people who said candidate A? It's 1,200 divided by 2,000, which is 0.6. That's the equivalent to saying 60%. All right, so the proportion is always expressed as a decimal. So suppose we wanted to create what's called a bootstrap sample derived from this original sample. Suppose we create one. And now we see 1,205 out of the 2,000 say they will be voting for candidate A. Well, 2,000 people are the same 2,000 people as in the original sample. They haven't changed. But what we're doing here is we're sampling, we're taking another sample, and we're using what's called sampling with replacement. Sampling with replacement means that once we choose somebody from the original sample, we put them back into the sample, and then they can be chosen again if it's possible to be chosen again. They could be chosen again. That's obviously not true in a real sample, a real survey, where you just survey a person once, ask them the question, and then that's it. That's called survey without sampling. Excuse me, that's called sampling without replacement. But what we'll be doing when we create a bootstrap sample is sampling with replacement, which means we will choose somebody from the original sample, we record whether they like candidate A or like candidate B, and then we put them back into the sample, and we let a computer generate the next person, randomly select another person, and it could be the same person again. So in this case, 1,205 means that there are people in the sample that were chosen more than once, okay, who voted for candidate A. And there will be some people who were not chosen, who voted for candidate B. So it's like that, all right? So that's called bootstrap sampling, sampling with replacement. And every time we do a bootstrap sample, we'll get a different amount. Here's 1,199 people saying they would vote for candidate A. We'll choose another one. This time 1,217 are choosing candidate A. So it will change from sample to sample. Notice down here, it plots each of these bootstrap samples for us. The most recent one is this one right here, 600. Nope, that wasn't that one. It was this one here. It's 1,217 out of 2,000. And then here are the other two that we plotted. We can do a few more. And the bootstrap sample shows up here as the most recent one, but we can choose any of them by just running our cursor over those dots. Each dot represents a sample of how many? 2,000 people, each sample. And each sample will have a different, most likely a different sample proportion, all right? Bootstrap sample proportion. So let's create another 100, another 1,000. Suppose we have 1,107 samples altogether. All these black dots, each one of these represents one of these bootstrap samples of size 2,000. Each one of them could have a different count and a different proportion, right? The count meaning the number out of the 2,000 who voted like candidate A. So there's 1,107 of these samples here. And if we wanted to create a confidence interval, we just click the box there for two tails. Notice in the middle here it says 0.95. That represents the confidence level. If it's usually represented as a percentage, so we would multiply that number by 100, and we would get 95% confidence interval. All right, that's the way to describe this, 95% confidence interval. It runs from a low of 0.58 all the way up to a high of 0.622. Now, how many black dots are within this interval? It's easy to find out. You just take 0.95 and multiply by the number of samples, 1,107 dots or samples. And that gives you the number of samples, bootstrap samples that are inside this interval. The number that are outside the interval, well, that's just simply 5% or 0.05. The difference of the sum of these two numbers, or the difference between 1 and 0.95, that gives you the number of red dots outside the interval. In this case, it would just be 5% of 0.05 times 1,107. That gives us the number that are outside the interval. How do we interpret this? Well, one way of interpreting that is incorrect, right? An incorrect way of interpreting this is to say there's a 95% chance that the true population mean is in between 0.58 and 0.622. That's not what this confidence interval is saying. It's not true, right? So when we say probability like that, that's not correct interpretation. A correct way of interpreting it would be we are 95% confident that this interval between 0.58 and 0.62 actually contains the true population mean. And what do we mean by 95% confident? We mean that if we ran as many of these samples as we could, thousands, millions of them, billions of them, we could estimate at about 95% of those intervals. All right. In other words, we would create a confidence interval for each of those sample means that we would come, or sample proportions that we would come up with. We would create an interval around it, just like this, and we would expect 95% of those intervals to contain the true population proportion, and 5% would not. So what we're saying basically is we're 95% confident, which means we're hoping that this particular interval that we came up with is one of the 95% that do contain the population proportion, and not one of the 5% that do not. All right, so that's what we mean by 95% confident. Okay, any questions about that? So it's not a probability. It's basically, it's based on the idea of repeating this process many, many times and determining that about 95% of the time, the particular sample would contain the population proportion, right? But it's not a probability. Okay. Any questions about that? Okay. All right. So that's how we do a confidence interval for a population that estimates a population proportion. This is through what's called bootstrapping. It's a computer simulation. It uses the original sample that we have. There's just one sample, and derives these additional samples called bootstrap samples using sampling with replacement. And we create as many as we want, all right, thousands of them. And then we hit the button here, two-tail button, we create a confidence interval. Now, every time you do this, you reset it and did it again, you would get a different answer. But the confidence interval should be pretty close to each other, even if you repeat this process, but you'll get a different group of dots here. So in the particular test or quiz that I'll be giving you today, I'll be displaying a particular one of these plots to you for each of the questions, and then ask you questions about it. All right, any questions? All right, so what we're going to do now is also do an example of a confidence interval, bootstrap confidence interval to estimate a population mean. So we're going to click this one right here, right? And notice it says bootstrap dot plot of the mean, so that's what we want. So suppose we, let's just choose something here. Let's choose the Manhattan apartments that are being rented. Okay, so this is a sample that we got of 20 apartments. N is 20, which means 20 apartments. The original sample. Notice in the original sample, there's a mean. Now, what is the mean of it? This is in Manhattan, New York, so it's expensive. So these are monthly rents, monthly rental prices for apartments. There's 20 apartments that were randomly selected out of the thousands that are in New York. And each one of these apartments has a different rental price. Here's one that's $5,495 a month. There's one that's $4,050 a month, and then there's others that are much cheaper. Here's one that's $1,927 a month. Those are the cheapest ones. So here are 20 of these, and we average them, and we come up with $3,156.50 is the average rental price for the 20 apartments that we chose at random. Okay. And actually, there's one all the way out here, by the way, $7,800. This is a very expensive apartment, $7,800. All right, so we're going to choose one bootstrap sample to show you what it looks like. Okay. It also chooses 20, but again, it samples with replacement, which means once it samples one of the apartments out of this here. That apartment gets thrown back into the sample, and then you randomly select another one, and it could be that that first one gets sampled again. Well, as you can see, the 20 get sampled this time. There are none of them that are in between. There's no $4,050 apartment that didn't get sampled in the Bootstrap sample. This one for $54.95 didn't get sampled. It's missing. This one for $7,800 did get sampled. Notice it's here, but some of the ones on the lower end got sampled more than once. All right, so these 20 plus the one all the way out here, if you average them, comes out to $3,030.55 is the average for this one Bootstrap sample. And you can create another one that has another group of 20 out of the original 20. Notice here that, again, the $4,050 apartment is missing in the Bootstrap sample. But this one for $54.95, notice it was picked twice. All right, picked twice. So this one out here was picked again, $7,800, and then there's the other 17 are on the lower end. This one has a sample mean of $3,029.45. Now notice again, for the original sample, we have the sample size, which will be the same for both the original sample and any of the Bootstrap samples. Notice each of these have a mean, sample mean, the original sample mean, Bootstrap sample mean. There's a median price also, $29.16, $23.25. So there's median prices. Standard deviation price of the prices, the 20 prices are also listed here. I could, in a quiz, I can ask you, if I just displayed these, I could ask you any of these, mean, median, or standard deviation, for either the original or for the Bootstrap that's being displayed. So let's just generate some more here. All right. In this case, I have 3,432 samples that I've selected. Okay, so all these dots here, there's 3,432 of them altogether. Each one of these has a sample size of 20, and they are sampled from the original sample of 20 using sampling with replacement. Again, if I wanted to create a confidence interval, okay, and look what happens. I get a confidence interval, and I'm going to change actually the level of confidence. I'm going to make it, instead of 95, I'm going to make it 90% level of confidence. I'm now decreasing the level of confidence. Now look what happens when I decrease the level of confidence. The interval becomes narrower. All right. Now lowering the level of confidence means I'm not as confident as 95%, which means if I did this process over and over again, 90% of the intervals would contain the true population mean in this case, and 10% won't. But the interval is more narrower, which is good. I want the interval to be narrow if I could have it narrow. But that's the trade-off between level of confidence and how narrow it is, okay? The lower the level of confidence, the more narrow is the interval, which is good, but lowering the level of confidence is not as good. If I increase the level of confidence, for example, if I change this to 0.99, notice that the interval becomes wider. It's wider than it was before. So increasing the level of confidence is a good thing. Okay, but it results in a wider confidence interval, which is not as good. So most people, when they do research, pick 95% confidence level because it's sort of a balance between level of confidence and how wide they want the interval. And so they don't go for 99% typically because the intervals are too wide. And they don't go for 90% typically because level of confidence is not high enough. But this is what the 99% confidence interval means. And in this case, you would say with 99% confidence, the true population mean is in between $2,464, and I guess you would have to round it here, 18 cents, and $4,076.32, something like that. How many dots are inside this interval? Well, it's 0.99 times 3,432 dots, gives us the number of dots within the interval. And then since 1% is left, half over here and half over here, you would say 0.01 times 3,432 gives us the number of bootstrap samples that are outside the interval. All right, so it's pretty easy to calculate these things. All right. And I could also, of course, yes, go ahead. Question? Oh, all right.
I was gonna say, can you repeat that again, like with the calculation method?
Oh, all right. Well, if you want to calculate the total number of bootstrap samples in total are shown right up here, which is samples. That's the total number of dots or samples. If you wanted to know the number of dots or samples within the confidence interval, basically it's the number of black dots here. You would multiply, in this case, 0.99, this number, times 3,432, and that gives us the number. If you wanted to know the number that are outside the interval, it's simply 0.01, which is the difference between 1 and 0.99. 0.01 times 3,432 gives us the number of red dots outside the interval. Kind of makes sense, right? Common sense, that's what you would get. All right, any questions about that? Okay. Now, we're going to start our quiz in about 8 minutes or so. I do want to show you 2 more types of intervals. Now, what I just showed you was a review, and it was for a confidence interval for a single mean or a single proportion. But what if we were interested in looking at 2 populations? We take 2 samples for 2 different groups, and we want to know the difference in their proportions or their difference in their means. All right. So we subtract their proportions or subtract their means. So let's look at confidence interval for difference in proportions. And I guess we'll use the one that's given to us here. So here's the original sample. There are 2 groups. All right. And what's being measured is what is the number of text messages. So if you're asking basically each person who's in the survey, how many text messages do you have? I guess that's what, yeah, I guess that's what you're being, or wait, maybe you were being asked, not the number of text messages. You're being asked if you text message, period. If you use text messaging. Now, obviously, everybody does now, even adults do now. But this is, this data set comes from, maybe 10 years ago, maybe when some adults were not text messaging at all. So, so think about that for a minute. So we're just asking each person in the survey, do you use text messaging with your phone, with your smartphone? And so let's see how many people were actually asked this question. Well, 800 teenagers were asked this question, and 2,252 adults were asked this question in the original sample. All right, you see that sample size? There's a sample size for the teens, sample size for adults. All right. So of the teens, 600 out of the 800 teens, 696 of them said yes, they use text messaging. And out of the 2,252 adults in the survey, 1,621 of them said yes, they text message. Now, how do you come up with the proportions? Very easy. The count divided by the sample size gives you the proportion. 696 divided by 800 is 0.87, or 87%. 1621 divided by 2252 is 0.72, or 72%. All right. So if for in this original sample, we would say that 87% of teens text message, 72% of adults text message. That means 15% more teens in the sample text message than adults. All right. You subtract these 2 numbers. 0.87 minus 0.72 gives us 0.15. All right. Now, what are we assuming here? We're assuming that there's two groups. We're calling one group group 1 and the other group group 2. And I believe, I'll double check this when we actually do the bootstrapping here, but I believe that group 1 is the teens that are listed here, and group 2 are the adults. All right. So 0.15 is the sample proportion, or the sample difference in proportions between teens and adults. So the P with the little hat above it, the P1 hat, refers to 0.87 for the teens, and the P hat 2 is referring to the 0.72 for adults. Okay. Any questions about that? All right. So we're subtracting the two proportions. That's what we're doing. All right. So what are we going to do now is we'll create a bootstrap sample. Notice that the bootstrap sample now has to deal with two groups. We do sampling with replacement for both the teen group and the adult group when we come up with our counts in the bootstrap sample. So we still have our 800 teens and we still have our 2,252 adults in the bootstrap sample. But again, we sample with replacement for each of these groups to come up with our different counts for each group in the bootstrap sample. And then we just divide again to come up with these proportions. Now, in this case here, the difference is close to 0.15, but if we ran another one, we'd probably see something different. Yep, here's one where the teen count was lower in the bootstrap sample, which means some of the teens were not who do text message were not counted in the bootstrap sample, and then more adults were counted in their bootstrap sample. All right, so the sample proportion for teens went down from the original sample, but it went up for the adults. The difference is 0.132 this time. And that's, of course, what we're measuring, the difference between the two proportions. And it shows up here, right? It shows up, here's the 0.132, here's the latest one, and then here's the first one that we did. We just generated another 10 of these, another 100 of these, maybe a few hundred of these, another 1,000 of these. All right, so now we have 1,312 samples. Right. And what do each of these dots represent? Each of these dots represents the difference between the proportions for the teens and the adults. All right, 0.15, for example, says that there are 15% more teens who text than adults text. If we run our cursor out here, where it's 0.174, that's 17.4% higher proportion of teens than adults who text message. Right, so it's showing basically the excess. All right, and now there's 1,312 of these dots representing the difference in those two proportions. We would create again our confidence interval. Notice the confidence interval is a let's make this a I'll just choose something else this time. I'll make it a 93% confidence interval, 0.93. So the interval is now between 0.123 and 0.178. So the way to state this, the interpretation is a little bit different now. We would say something like, we're 93% confident that the difference in proportions, difference in proportions between teens and adults is between 0.123 and between 0.178. And we could do the same thing with means, the difference in means. Okay, we could find, for example, in this data set here, this has to do with number of hours of exercise between males and females. What are listed in this chart are all the hours that each person exercises per week for males. How many males? Now, group 1 in this case are males. It's this group here. Group 2 are females, the one above them. N1 represents 20 males. There's 20 dots here. Group 2 represents 30 females. There's 30 dots here. We take now we find the mean of these dots. So for the males, we average these 20 exercise times and we get to 12.4, an average exercise amount per the time per week, 12.4 hours. And for females, it's 9.4 hours difference. And if we subtract those two, that's where we get the 3 hours difference between group 1 and group 2, which is male is group 1, female is group 2. Again, we can create 3,000 of these differences in the means. We click here, and we would say there's a 95% level of confidence that the difference in the means is between negative 1.567 hours and 7.6 hours. Now, this negative number here represents that females actually exercise more than males on average, because it's a negative number. But the 7.6 says that males average more by 7.6 hours. So we would say with 95% confidence that the true difference in the exercise times between males and females is between these two numbers here. All right, so it is 4:10 now. So it is time for your quiz. I'm going to stop sharing, and I'll stop the recording. So you can go ahead and open up your quiz. Again, you have 30 minutes for those 30 minutes to complete the quiz. And you can, if you have any questions, or you can, of course, send me a chat. Please don't yell out or anything during the quiz, because that would be disturbing.